Do you check your blood sugar and check it often? Then this video is for you. Today we're going to talk about actual sugars. So we have sugars, carbohydrates, or saccharides. They all pretty much mean the same thing. They are sweet molecules composed of carbon, hydrogen, and oxygen. Now the word carbohydrate, of course, comes from the ancient Klingon, carbo for carbon and hydrate for water. So what we get here is a ratio of carbon, hydrogen, and oxygen. Predominantly with the hydrate water part, there are 2 hydrogen atoms per every oxygen atom within a typical carbohydrate molecule. By far the most recognizable sugar in the world is this disaccharide here, sucrose. It's common table sugar. A gajillion tons of it are produced annually, and people like myself probably eat a whole bunch too much of it. As the name suggests, the disaccharide sucrose means it has a monosaccharide glucose molecule here on the left and a monosaccharide fructose molecule there on the right. Now it's connected in the middle by this bond called a glycosidic bond. It's really just a special name for a covalent bond that links a carbohydrate molecule to something else. Now it doesn't have to be a carbohydrate to which it's linked, but usually it is. Now you may look at this sucrose molecule and ask yourself a bunch of questions, like what's going on with all these OH units, these CH2OHs, why does the glucose have a 6-membered ring and the fructose has a 5-membered ring, and believe me, we'll get to all of that. For now, let's just have a couple fun facts about sucrose. First, you can mix sucrose as a fuel with potassium nitrate as an oxidizer, and it's called rocket candy. It's used in amateur rocketry to make little rockets go up. Also, you can mix sucrose with very concentrated sulfuric acid and get a reaction called the black snake. Make sure you look that one up. Breaking down sucrose into its 2 pieces, we start with the monosaccharide glucose. Glucose is the sugar that the body uses to get a lot of its energy, and it is stored as a long-chain polymer called glycogen. Glycogen and the other carbohydrate polymers are a discussion for a whole nother day in relation to the elixir of life, beer, and if I ever get around to that video, I'll post a link for it somewhere here. Glucose was first isolated in 1747 by Andreas Marggraf, who also did some inorganic research extracting phosphorus from urine. We will not be talking about that. Glucose is an aldohexose, meaning there are 6 carbons in the molecule and that it has an aldehyde group. But Devin, I don't see no aldehyde group back here. And you'd be absolutely right. There's no aldehyde functionality shown here. The reason is that we're projecting this glucose as a cyclic molecule, meaning there's a ring structure here. You can draw these monosaccharides in a few different ways, and this is called the chair conformation. It comes from the fact that if our ring structure were planar or flat, all of these substituent OHs would have a lot of strain associated with them. They would be far too close together, and like the same ends of magnets, they would want to push away from each other. So the way we minimize what's called ring strain, being that you're flat and you have a lot of that strain of your substituents there, is we soften that and we turn that ring into this chair conformation. It allows all of these groups to be as far away from each other physically as they possibly can be. This is the most thermodynamically favorable conformation. In its linear form, you can finally see the glucose 1, 2, 3, 4, 5, 6 carbon, assuming that at all of these intersections there's a carbon that I just haven't drawn, with the aldehyde structure at the top, aldohexose. This representation is a very specific one called a Fischer projection. At each one of these intersections, you can see the OH is facing on one particular side of the line going from the aldehyde group down to the carbon at the bottom. That's not by accident. The Fischer projection, again, is a very specific, not haphazard way to draw each one of these OH groups, where especially at the bottom one here, if we switch this OH and move it to the left of the line instead of the right of the line, we get a completely different configuration of glucose. We'll talk about all that in a little bit, but suffice to say, again, the Fischer projection is a very designed way to draw a monosaccharide in its linear form. We can also show the other cyclic representation of glucose called the Haworth projection, shown here. At one point in the filming of these videos, I got paranoid about how I was pronouncing Haworth projection, and it turns out you could also say Haworth or Haworth or any number of different things. I'm gonna say Haworth projection, and if you disagree with me, you can watch somebody else's YouTube video. Much like that Fischer projection, the Haworth projection has the lines of the OHs being very distinct, either straight up or straight down. Again, this is not by accident, where if I take this OH over here and instead of being straight down, I make it straight up, that's a completely different configuration of glucose. If I take one of these ones and change them from being straight up to straight down, it's not even glucose anymore. So again, this representation is very distinct and very purposeful. Converting between the Fischer projection and the Haworth projection and the chair configuration on top of that was just a giant pain in the ass in my biochemistry course in college. And because this is my YouTube channel and I don't want to talk about it, I'm not gonna. I'll close out glucose by saying sometimes you'll hear the Haworth or the chair configuration referred to as a glucopyranose structure. Really all that says is the six-membered ring in here with the oxygen in one of the positions is called a pyranose ring. So the glucopyranose is just the six-membered ring configuration cyclic structure of glucose. That's all that's saying. Now we can see the other half of the disaccharide sucrose, the monosaccharide fructose, or fructose, whatever the hell that is. Now, allegedly, fructose is the worst molecule in the world. If you read anything about health and fitness, fructose is responsible for like 99% of all bad things that happen to humans. Either way, I've shown both the Fischer projection and the Haworth projection here for fructose, and we can see the biggest difference between it and its brother, glucose. While glucose is an aldohexose, fructose, still a hexose, 1, 2, 3, 4, 5, 6 carbons, is instead a ketohexose. So instead of the aldehyde being on the end, we have a ketone in the middle. So this ketone group, when it cyclizes, changes fructose from being a six-membered ring into a 1, 2, 3, 4, 5 membered ring in the Haworth projection. So now we get into just a little bit of organic chemistry. Before I forget, you remember that time we were talking about the cyclic structure of glucose and how it's called a pyranose, specifically glucopyranose? Yeah, same thing applies to fructose, except the five-membered ring with an oxygen in there is called a furanose. So this, the Haworth projection of fructose, is called fructofuranose. Now back to your regularly scheduled program. Here you can see that I have numbered each of our carbons in both the Fischer and the Haworth projection, and we're going to do the arrow pushing mechanism. Now I can't resist this, even though I said I really wasn't going to get into this, because I want to show off how bad I am at arrow pushing, and this is about as difficult as it gets. Anything more than that, Devin's calling it quits. Each one of these oxygens that you see participating in our little reaction have these lone pairs of electrons. And what's going to happen is this OH here, this oxygen, is going to spring its electrons up and hit right there. The electrons from there are going to spring back there, which means that oxygen is only going to have one bond instead of two bonds. So it's going to have a negative charge. This oxygen is going to have a positive charge because it has a bond on the hydrogen, the carbon, and the other carbon there. So that guy's going to essentially come over here and boop, pick that hydrogen. Hydrogen's going to donate back its electrons, and we're going to get over here the ring structure. So now again, you can see that the number 5 carbon oxygen is going to attack. So that turns in that oxygen is that one right there, and the carbonyl, the ketone oxygen, pulls an OH off of that number 5 OH and becomes that right there. Make sense? Fructose is also, as the name would suggest, a large part of high fructose corn syrup. Now that starts as regular old starch, kind of like cornstarch that you'd find in your cupboard at home. And the first step of getting to high fructose corn syrup is called acid hydrolysis. Now instead of me drawing a million long chain of molecules to get to that starch molecule or starch polymer, I'm just going to throw up this guy, a disaccharide called maltose. And maltose is a disaccharide of 2 glucose monosaccharides. So while the sucrose was a disaccharide of 1 glucose and 1 fructose, here the maltose is just 2 glucoses. And we're looking very specifically again at this special covalent bond called a glycosidic bond. When I bring an acid H+ proton in here, at least a Bronsted-Lowry acid, which we don't need to worry about all that. When I bring my acidic proton in here, I again have these little lone pairs of electrons on my oxygen, and one of these is going to come over and just attach right to there. Cleaning that up a little bit, and we end up with an oxygen that is covalently bonded to this hydrogen here. The important part now is that this oxygen has 3 bonds, 1 each to 2 carbons and 1 to this hydrogen that it just got from the acid. That gives it a positive charge, so it wants a little bit of negative charge back. So if we come over to this carbon and give all of its electrons back to the oxygen, we then end up with an oxygen that's now neutrally charged because it's only bonded twice, 1 to the hydrogen and the carbon, but we have this positively charged carbon over here that doesn't have enough bonds. This is where the hydrolysis part of acid hydrolysis comes in. If we bring a water molecule into the mix, we can see that these electrons from the oxygen of the water attack that carbon. It becomes neutrally charged, so we get rid of that positive charge there, and this hydrogen is going to give all of its electrons back to the oxygen, leading to This, our final situation where we have two of these OHs connected to the separated glucose units and our acidic proton left over to do that whole process over again. This is how we start with starch and via that acid hydrolysis process end up getting to a point where we have a whole bunch of those glucose units. The question now becomes, how do we go from glucose to fructose? Well, as it turns out, that's a little more biochemistry than I want to get into right now, so we're not going to talk about the exact process, but suffice to say that after my acid hydrolysis and a little bit of enzyme action, I've got my glucose pieces. Then I use glucose isomerase, another enzyme that again goes through some biochemistry we don't want to talk about, turns everything there into fructose. From all that fructose, there's a little more purification, and you end up with high fructose corn syrup that you can drink and die. If you've been paying attention, which if you haven't been, why are you even watching this? You'll notice that fructose and glucose have the same molecular formula, C6H12O6. The difference, principally, is in that carbonyl position, where in fructose the carbonyl exists as a ketone in position 2, where in glucose it exists as a terminal aldehyde, has to be terminal to be an aldehyde, in that first carbon position. Now let's make it difficult. This is galactose, the last monosaccharide and real sugar that we're going to talk about in this video. Now, if you aren't an expert in Fischer projections, you would think that this molecule probably looks pretty close to glucose. And let's be honest, if you are an expert in Fischer projections, you probably hate this video. And you'd be wrong, but it's close enough. And this is glucose, which we've drawn again. And here you can see that there really isn't much difference between galactose and glucose, where if we zoom in on this C4 carbon here, the OH in galactose is to the left of the center line, and the OH in glucose is to the right of the center line. Now, if you were a smartass, you'd probably say something to the effect of, "Don't single bonds have free rotation around the middle there, so they're the same molecule?" And you'd be almost right. The problem is, glucose and galactose are excellent examples of stereoisomerism. It's a concept in chemistry called chirality. Now, if we wipe the slate clean here and start with something very simple like carbon, we can see a couple things that stand out here. If I take my carbon and I bond it to 4 different hydrogen atoms, I get CH4 or methane. Now, if you look at this in the plane of the whiteboard here, I can draw a plane of symmetry vertically or horizontally, such that the left hydrogen is the same as the right hydrogen, top hydrogen same as the bottom hydrogen. Now, in reality, this molecule doesn't exist like this flat in the plane of the whiteboard. One of these hydrogens is coming out facing you toward the camera there, and one of them is facing back into the plane below, or kind of back from that whiteboard. It exists three-dimensionally because each one of these atoms, the hydrogens attached to the carbon, want to be as far away from each other as they physically can. However, all that being said, because the groups are all the same, they're all considered equivalent, and with the planes of symmetry, this molecule can be rotated about these single bonds in any number of different ways and is considered the same molecule. To illustrate the other side of this, it's easier just to make an example, where if instead of the 4 hydrogen model, I do 1 hydrogen and I put 1 fluorine here, a chlorine here, and keeping with the halogen theme, I put a bromine there. Because each of these 4 groups is different from each other, this molecule creates what's called an optical center, or a stereoisomer. They're all just fancy words to say something to the effect of this molecule exists in 2 forms, both of which are non-superimposable mirror images of each other. The easy way to deal with that sort of weird phrasing is to think of your hands. They are absolutely mirror images of each other. Right hand, left hand, mirror images. But you can't superimpose them. You can't overlay them on top of each other in a way that they actually overlap. You'll always get something that looks a little different, even though, again, they're absolutely mirror images of each other. This molecule exists the same sort of way. There are 2 different sets of it called enantiomers. In our sugar examples, all of our monosaccharides, glucose, fructose, galactose, etc., exist like this molecule in that they have at least a couple different enantiomers. Because of their stereoisomerism and chirality, sugars in their linear form at least exist in 2 types. The first, L, or levo in Latin meaning left, has the OH on this carbon facing the left of that center line, and the other one, D, dextro, you guessed it in Latin, right, has the OH of course on the right side of that center line. What's interesting is the body can only metabolize this D isomer, so D-glucose is the only one that our human bodies can use. For some reason, L doesn't work, and it goes into some biological concept called the homochirality of life. That leads to all sort of metabolic pathways like the one that you can see here. And, wow. So galactose. If you take galactose and make a disaccharide out of it with glucose, you get this molecule here, lactose. Now lactose is the principal sugar in milk, and again, it's a total plug, but if you check out my video with beer and sugars and all that sort of fun stuff, you can see how lactose plays an interesting role in the taste of some particular beers. Your interesting fact about galactose is that it exists as a disaccharide called galactose alpha-1,3 galactose. Now, it's in mammalian tissue like beef or pork, but does not exist in mammalian tissue like primates, of which, you guessed it, humans are a part. Now, this galactose alpha-1,3 galactose, colloquially known as alpha-gal, if a tick were to bite a cow and then bite a human, it could impart some of that alpha-gal into the human system. Then an immunoresponse is created that's basically like an allergy, and then you're now allergic to any tissue that has that alpha-gal in it, which includes like steak and pork and pulled pork and ribs and all sorts of delicious stuff. So not only is it bad enough that ticks cause Lyme disease all over the place, now we can't even eat our steak. And there you have it, a super exciting discussion about real sugars. We got into carbohydrate naming, structure, differences among them, chemistry involved with carbohydrates, and some interesting facts about each of them. Stay tuned for part 3 of the video series where we get into fake sugars, and specifically we start talking about sugar alcohols. See you there.